Let's look at some of the world's landscapes. The Grand Canyon in northern Arizona. Let's compare this with some other landscapes. Say the Valesian Alps in southern Switzerland. The desert around the petrified forest in the western United States. The valley of a small stream on the North Yorkshire moors, England. They're all very different, each formed by a particular set of environmental conditions and by a different pattern of weathering and erosion. And yet, they all have one thing in common. They're all made up of slopes. Steep, almost vertical slopes. Rugged slopes. Smooth slopes. Gentle slopes. Almost flat slopes. Yes, even land as flat as this part of East Anglia contains a complex pattern of slopes. In this programme, we're going to concentrate on one type of slope in one area, the English Lake District. These are comparatively recent slopes, and they've formed on very hard rocks. This type of slope is very different from the slopes found in lowland areas, a point we will return to later. This is a typical Lake District landscape, and even to the untrained eye, the slopes display a degree of order. There are, for example, many vertical faces like this, and below the free face, slopes tend to be very steep, like this. While towards the valley floor, there are very gentle slopes. Together, such slopes produce this distinctive curved shape, this concave profile. We're going to take one of these slope elements, the steep slope below the free face. In Langdale, such slopes tend to dominate the landscape. Here, in our study area, they're less impressive but more approachable. That's why we have chosen them. We can now look at these slopes in detail. The free face is obvious. It is solid rock. The slope below is steep, and it's formed from debris, very large debris at that. It is in fact scree material, large rock fragments produced by the weathering of the free face, and it piles up at a characteristic angle. We can see what happens in the laboratory. This is a model of a scree. The debris has piled up at the base of the free face, forming a scree slope. The angle of the scree slope is about 45 degrees. More debris falls onto the scree. Watch what happens. The entire scree slumps. Let's look at that again. The scree has obviously become too steep and has collapsed to assume a lower, more stable angle. This time the angle is about 32 degrees. Screes are obviously an important element in the Lake District landscape. We might expect, therefore, to find many slopes in our study area at angles of 30 degrees to 35 degrees, the critical angle of rest of scree material. We can test this hypothesis simply by measuring a large number of slopes in the study area and by plotting the distribution of their angles. Study slopes are chosen at random, using random number tables.
Right, I want you to take two random numbers from your random number tables. One will tell you your compass bearing, and two will tell you the number of paces. Find the direction you're going on your compass and start walking off in that direction. Okay, so would you like to do that now?
Just that way over there. And it's 87.
Right, open your mind.
And you're going that way. Good.
You can do it.
This location, selected at random, marks the starting point for our first profile measurement. Before we start, however, what is a profile? A profile is a line which cuts each contour at right angles. In the field, it would be the line described by a boulder rolling down a hillside. Sometimes a profile is a straight line. Sometimes it is curved. For ease of measurement, profiles are divided into short lengths or facets. In this case, in an area of relatively short slopes, a facet length of 5 meters is used. In an area where long slopes predominate, longer facet lengths may be used. For each facet, the slope angle is measured. Here, a clinometer is being used. It's sighted on the eye line of the second member of the team. This is accurate enough for this type of survey, although the use of surveying poles would obviously give improved accuracy. When one facet has been measured, the team move upwards along the line of the profile. When the profile has been completed, a new one is chosen, also at random. The measurements involved are very simple, and they can be carried out in many ways.
24.
This, for example, is a very cheap type of clinometer, a protractor with a ball bearing moving freely in a groove or channel. A surveying pole is being used for sighting, and when the bearing comes to rest, it marks the slope
24.
angle. And this measuring frame can be made in any school. It's placed on the slope. There's a spirit level on one of the uprights. This is used to establish the vertical plane. The top of the frame, it's obviously running parallel to the slope, cuts across a protractor bolted to the upright. This marks the angle of the slope. Here, 21 degrees. Hundreds, even thousands of facet angles can be measured in a relatively short time, and all of this data has to be processed. Here we are using the Geography Today software pack, specially designed to accompany this television program. Facet angles are entered using the keyboard. They're then automatically retained on file. Once stored, the information can be displayed and analysed in a variety of ways. We are interested in the relative frequency of facets with angles between 30 degrees and 35 degrees in our study area. This is best shown on a histogram. There is a peak at 33 degrees to 36 degrees, but there are also two larger peaks, at 9 to 12 degrees and at 24 to 26 degrees. We must now try to explain these. To do this, we must go back to the landscape. In our study area, the screes are often exposed, but lower down the slope they disappear under a cover of turf. We remove parts of the turf cover, remembering to replace it afterwards. And just below the surface, we find typical scree fragments, but now there's soil mixed in with them. It is, in fact, partly weathered scree. Let's look at the effect of weathering on the development of a scree and on general profile shape. This is a model of a scree. The loose debris, its size carefully selected to match the overall scale of the model, is piled up at the foot of a free face. The fragments are generally large, and the angle of rest is about 32 degrees. The scree is exposed to heavy rainfall, such as that experienced in the Lake District. This storm, in fact, represents a 100-year rainfall event. In other words, a storm so intense that it's likely to occur only once in 100 years. Runoff is heavy on the free face. But on the scree itself, the rainfall appears to have little or no effect. In fact, the rainwater passes down through the pore spaces between the large scree particles, and the scree remains stable in spite of the intensity of the rainfall. Now imagine that the scree has weathered. We will model this by adding a fine sand and shingle mixture to the surface of the scree, like this. Notice that the angle of the scree is again about 30 to 35 degrees. But what happens if we have another storm event? The scree is again exposed to very heavy rain. Now watch what happens. This is mass movement, slumping on a large scale. The pore space is now partly blocked with fine material, filled with water, and the surface layers become unstable and slide down the slope. This type of mass movement is one of the major processes at work on the hill slopes found in our study area. This is the profile produced, the free face. The scree exposed once more by the removal of the fine material. And a low-angled slope formed at the base of the scree. This entire profile is now stable, even in a 100-year storm event. And it is, of course, a profile which is common in the Lake District. Let's look in more detail at how such profiles have been formed. Debris falls from a free face. It piles up to form a scree. The angle of rest about 32 degrees. This scree is generally stable at this angle. The scree surface weathers and breaks down to form fine material, which mixes with the larger scree debris. Under heavy rainfall conditions, this surface layer may become unstable, and the fine scree soil mixture slides down the slope in a sudden mass movement to assume its own angle of rest at about 22 degrees. This slope is again stable. Further weathering, and the surface breaks down into even finer material. Once again, heavy rain can cause the slope to become unstable, and further mass movement takes place. The fine material slides further down the slope and assumes an angle of about 10 degrees. (10, 22, 30). Angles which coincide with the peaks on our histogram. Here, here, and here. The slopes in our study area appear to have been formed by mass movements of the kind described. We might expect, therefore, to find a relationship between facet angle and size of debris. Let's examine this hypothesis. This is certainly scree. Notice the large angular debris. A sample is also taken lower down the slope. Here there is a cover of turf. This is removed. A mixture of angular scree material and fine weathered material is exposed. This could be the scree soil mixture of the model. Finally, the lower slopes, just above the valley floor. Here, scree material is completely absent, and we are dealing with nothing but fine weathered debris. To establish more accurately the relationships between slope angle and particle size, many samples would be needed, and each one would have to be dried, sieved and ground to give a mean particle size. For our purposes, however, a visual comparison is sufficient. Scree on the right, mean slope angle 32 degrees. Scree soil mixture in the center, 22 degrees. Fine material on the left, 10 degrees. So far, we have seen that the weathering of rocks tends to produce slopes with a marked concave profile. But all the slopes in the study area are not concave. Many of the slopes leading down to the stream, for example, appear to be straight or even convex. Are they? Let's test this hypothesis. For this, we measure two types of slope, those with streams at their base and those without. These will form our two categories. The actual profile locations are again chosen at random. Facet angles are entered into the computer. The sample identification, A or B, is given at the head of each column. If profiles are drawn, this can be done automatically using the Geography Today software, interesting differences emerge. These are slopes with no stream at their base. The profiles are obviously concave. A measure of the degree of concavity, this is the extent to which the profile deviates from the straight line, is also given. This figure can be compared with the same measure for slopes with streams at their base. Notice the difference in shape. Convex, virtually straight. The degree of convexity or concavity can then be used to test the difference between the two profiles. A test shows a statistically significant difference in profile shape between slopes with streams at their base and those without. What has caused this? It was the pattern of distribution of many facet measurements which suggested the processes at work on concave slopes, like this one. This is the distribution for slopes with no stream at their base. Remember, they are concave. Once again, there are three peaks representing scree soil mixture, and fine valley floor deposits. Compare this with a histogram for slopes leading down to streams. Now there are only two peaks, one at 24 degrees to 27 degrees and the other at 32 degrees to 35 degrees. In other words, 10-degree slopes at the base of the profile are missing. This suggests that streams remove fine material from the base of the slope, and it's the removal of this material that produces the convex profiles like these, which are typical of valleys with active streams in them. The slopes we have looked at are all recently formed slopes. Their form is largely determined by the nature of the debris produced by weathering. They are in fact often called weathering-limited slopes. Changes take place rapidly on such slopes. They become unstable and there is sudden mass movements. The scars left by such movements can be seen everywhere. In other areas, slopes are different. Where rocks are soft or where weathering has continued uninterrupted for a long time, the debris mantle can become very thick. The shape of these slopes is largely determined by processes like soil wash, soil creep and solution. These processes are slower and less dramatic than the mass movements at work on hill slopes like these. But in time, even these slopes could succumb to the effect of weathering and be reduced to profiles as gentle or rolling as those in East Anglia or the North Yorkshire moors.